Engineers and physicists often need to simplify complex problems to approximate solutions. This means when considering how light interacts with tissue, water is often used as an approximation. But we know it's a little more complicated than that. Visible light can travel easily through water, but can barely travel through the tip of your finger. Take the light on your phone and place it on your fingertip. Does it look red? That's because most of the blue and green light is attenuated or reduced through scattering and absorption events, but red light can travel further. Real tissue contains blood, lipids, and other substances that scatter and absorb light, called chromophores. A chromophore is just a fancy word to say a substance that absorbs and scatters light in a particular way. Light interacts with chromophores in different ways, depending on the color or wavelength. These properties can be graphed as the probability of attenuation, y-axis, for different wavelengths of light, x-axis. Let's take a look at a few examples. Water, oxygenated and deoxygenated blood, and lipids, to show a few. As we account for more substances, we can begin to make a better estimate of how far light can travel before either is attenuated. These chromophores impact how far light can travel into tissue and how deep fluorescence emissions can be detected. Fluorophores that emit blue or green light will only be detected at very superficial depths, whereas red or near-infrared emitting fluorophores will be detectable at a greater depth. Since tissue is heterogeneous, some highly attenuating chromophores may obscure fluorescence either by reducing the excitation light or limiting the fluorescence emissions reaching the surface. These are all factors that need to be considered during fluorescence imaging, and why phantoms with tissue-equivalent optical properties are important for understanding the real-world performance of imaging systems.